All right, I just clicked record, so we should be recording. And what are we doing? We're working on the homework assignment, right? Or the lab. I'll answer questions about either one that people have. Actually, those are old formula sheets, so I can use them for scratch paper. Could I go over question 2? Okay, I better print the homework because I don't have these things memorized. And homework winter 2024. This is geometric optics, I think. I better get you a new assignment up for you. I'm sure you're looking forward to that. Okay, so yeah, 9 and 10, actually 9 and 10 are not optional. They're just things that you should probably work on. They're just extra practice. So especially number 10, that would be actually designing a telescope and a lens. So that might be a lab in itself almost. And number 10 is just extra practice because I don't think I'd given you a convex mirror problem, or we may not have done an example like that I recall anyway. Okay, so question 2. Oh man, do I have a front surface mirror here? Shoot, I don't think I do. That's what question 2 has to do with. And it's related to, well, anyway, the other day, Jorge was asking a question about this after class, and I happened to have a front surface mirror. I think he'd been reading about it. And on most of the mirrors that you see at home, they have a, if this is the front of the mirror, and this is the wall that it's attached to, so back there, the silvering is actually put on this side of the mirror. And the reason it's put there is because if it was on the front, if you were cleaning the window or something and you rubbed a little too hard, you'd scrape off some of the silvering. And so over time, that would degrade and the mirror would end up looking horrible. So they put it on the back. And it's just a real super thin layer of basically silver paint that they put on the back of there. It's not super high quality or anything, but with that kind of a mirror, if you hold something up to it like a pen, you'd have the tip of the pen sitting here, and you'd see the reflection of the tip of the pen over here. And you can actually see a noticeable gap between the tip of the pen and the back of the mirror. You can do that on a window at night. If you're in a lighted room and you hold something up to a window at night, it's kind of tricky to see, but you might be able to see that. And even if there's no silvering on there, there will be light reflected from it. It's like at night, if you're in a lighted room and it's dark outside and you stand up against a window that's looking out on the dark stuff, you'll see your reflection on the window. And so if you look at it really closely, you may be able to see an effect similar to what you have when you put a pen on a regular mirror. And you can just do that with a bathroom mirror and you can see a noticeable gap there. Try it out with a window at night and see if you see it. But a front surface mirror, and I've got some in the classroom, are some where the silvering is actually applied to the front surface, and you want that to be the case if this is the front. If you're concerned about the optical quality of the reflection, you might want that to be the case, where you don't want any interference from stuff that's reflected from the back and stuff that's, or from the front and reflected from the back, because that could foul up images. And they would put them in things like copy machines and good quality printers and scanners and things like that. But a front surface mirror, if you put a pen up against it or something like that, you'll see the reflection of the pen right there. There's no gap between them. Whereas here, you'd see the reflection of the pen back here, and there's a gap that's equal to the thickness of the glass. But a front surface mirror, that's what you have. And I've got a couple of them in the back of the room. I put them on stands. Next week, I'll do some demonstrations that'll let us see the interference of light, some of the interference and also diffraction effects. And what I do, I'll have the laser up in front of the room, shine it toward the back, have it maybe go through something that'll cause separation, like a two-slit pattern or something like that. And after it goes through that slide, it'll hit one of those mirrors. I'll have it set up like this, and the light will hit that, bounce over, and I'll have another mirror, and it'll hit that and come back to the front of the room, and I can display the pattern on the screen. And because it's traveled such a long distance, it'll spread out, and it's much more noticeable to see some of the effects that we're looking at. Whereas if the card was only a foot or so behind the slide that's causing the pattern, it wouldn't be separated enough to see very easily. So, but front surface mirrors. I've also got, I tried making a gadget one time it was kind of complicated, but it had a tilting mirror, and then it had a stand that was set like this, and I could put binoculars on this stand. And this tilting mirror, I could adjust the tilt of. And so with the binoculars, I'd be up here looking down in this direction through the binoculars, but I could look at stuff that was straight overhead and adjust the tilt to look at various things. And I had the whole thing on just a little plywood surface that I could sit on my lap, and it was stable enough to where I could easily look at stars straight up. Unfortunately, the front surface mirrors that I bought for it were real low quality, and they didn't produce good images of stars. Actually, the images of the stars kind of looked like little seagulls or something like that. And I've since bought what's supposed to be a much better quality front surface mirror, but I haven't gotten around to rebuilding this thing that I made for the binoculars. I'd like to do it for make it much larger so that I could use some large binoculars on there too. Okay, you will not lose points for not doing 9 and 10. No, they're just extra practice. They're not even, don't even turn them in if you do happen to do them. Okay. Going through 1 through 8 sounds like you've never looked at any of them, and so you don't have a clue. For every one of these questions, you should dig deep and try to figure that stuff out. For number 1, light requires about 8 minutes to travel from the sun to the earth. Is it delayed appreciably by the Earth's atmosphere? Well, what's the Earth's atmosphere made of? Okay, look that up. It's air, right? What's the index of refraction of air? Then how fast does light travel through the air? Compare that to the speed of light in a vacuum. And how thick is the atmosphere? How long is it going to take to get through however thick the atmosphere happens to be? So do a little bit of research on that and figure it out. Oh, let's see. Number 3 is just about a satellite dish. Think about where Well, actually, think about the concave mirror that we looked at for the big blue telescope the other day, and that formed an image of the clock. Where was that image? Okay. Turns out it would have been pretty darn close to the focal point of that mirror. The clock wasn't all that far apart, so you'd have 1 over s plus 1 over s prime is equal to 1 over f. That mirror had a focal length of just about 2 meters. I think maybe a little bit less than that. But the clock distance, oh, it was probably 8 meters away from the mirror, something like that. So that's not a super long distance. But if you do happen to have something that's a long ways away, like a satellite dish that's aimed at a geosynchronous satellite, those things have a pretty sharp curvature. They've actually got a short focal length, but 1 over s in the case satellite dish is going to be essentially 0 because it's looking at something that's what, 20,000, no, is it 20 million meters away? Something like that. It's a long ways. I can't remember what we figured out for the radius, orbital radius for a geosynchronous satellite, but it's far enough away that this is just about 0. And when that's the case, the S prime ends up equaling about the focal length. And so that's where the electromagnetic radiation is going to come to a focus. So think about that in answering that thing. Here's a hint on number 4. Look up the Lensmaker's equation, which is in section 34.4, actually. Yeah, they do call it the Lensmaker's equation. And just looking at the equation won't help. You need to read the derivation of it very carefully and find out what everything in that equation happens to be. And when you do that, you should be able to answer whether that equation would change if you drop a lens into water. So, okay. Dun, dun, dun. I had a guy that I would see at meetings once in a while, and he taught physics down at oh shoot, one of the community colleges in Oregon, and I can't remember if it was where or which one it was, but anyway, he was also a scuba diver, and he would take class to a pool, and some of them were scuba divers too, I guess, but if they weren't, they could just have a snorkel, and they'd do experiments with mirrors and lenses and things underwater and see how things worked out. He said underwater, you could make a lens out of a Ziploc bag filled with air because it would have a different, the air inside the Ziploc bag would have a different index of refraction than the water would. And so you could do experiments with things like that. That might be something fun to think about. Okay. Any other, talk about problem 6. Oh, that's a nice one. That's a proof. Yeah, consider 2 flat sheets of glass with indices of refraction N1 and N2, which are stacked on top of one another. Prove that it is impossible for light to enter one of the sheets of glass from air and subsequently undergo total internal reflection at the index with the second sheet of glass. Well, that might be interesting. For that one, you might want to be thinking about what if suppose you had air up here and glass. And it doesn't matter. The indices of refractions of glass are all around 1.5, 1.55 sometimes. In problem 10, there's some with an index of refraction of 1.56, or I mentioned that for it anyway. And you had a beam of light that struck right here, and I'll draw the normal. Okay, so here's an incoming beam of light, and this is the normal to the surface there. What will that beam of light do as it enters the glass? Be thinking about that. And then think about having, I'll call this glass 1 right here. Whatever that beam of light does, you'd have, this would be theta 1. It had been somehow, and whatever the index of refraction of glass happens to be, we can call it N sub glass. You could say that N air sine theta air is equal to N glass. Oh, I'm running out of paper. Sine theta glass. So you can figure out what that angle is going to be in the glass, but you should be able to just draw it roughly, without doing a calculation. This was stuff I went through on the very first day of optics. Okay, well then it's going to come down here and hit this interface, and I want you to show that it's not going to be bounced back. But think about what would happen if you had air here. What would happen when this beam of light that's been refracted at this surface hits the air? Okay, and is it possible for it to undergo total internal reflection there or not? So be thinking about that stuff. And it's a logic problem, more or less, but doesn't require any really fancy calculations, but you do have to know about indexes of refraction of air, what happens when light goes from a low index of refraction to a higher index of refraction, and then what happens when it goes from a high index of refraction to a lower index of refraction. When does total internal reflection occur? And what if instead of having air here, you've got another layer of glass instead? Can you have total internal reflection? And there's a clear answer to this. So that's that one. That's problem 6. And it's one gets you thinking about it. You don't have to look up anything in the CRC handbook. I think in the textbook, it's got a table with, whoops, that's the wrong chapter. We want to be in chapter 33 for that. Yeah, they've got total internal reflection there. Oh yeah, they've got index refraction for yellow sodium light, and they've got a bunch of different glasses. And for the glasses, they range from 1.52 up to 1.80. And it's just a bunch of different indexes of refraction. But there's a clear answer, no matter what the indexes of refraction of the glass happen to be. So see if you can do those things. Anyway. Okay, can I go over number 5? What is number 5? Oh, okay. That's just using this equation. N1 sine theta 1 equals N2 sine theta 2. But you use it at least 2 times. You'll use it at this interface, and then you'll use it again at this interface. And so and you have to recognize some things like if you have parallel lines and you have something that cuts them, then this angle is going to equal this angle. So you have to know things like that. But it's just a matter of using Snell's law a couple of times. And so that's the way to solve that. And let's see, assume on the diagram here, I only labeled that angle as 20 degrees, which is only 1 sig fig, but assume it's 20.0 degrees. So that's the angle it'll make there. Actually, in this case, you'll be sort of working backwards. You know the index of refraction of linseed oil, I think. Yeah, it's 1.48. So you know the index of refraction here. So you could call this N1 sine theta 1 if you wanted to. And then this would be N2 sine theta 2. If the light was going the opposite direction, it would bend exactly the same ways. It follows the same path. So it doesn't matter which direction it's going, that N1 sine theta 1 N2 sine equals N2 sine theta 2 is going to work either direction for the whole travel. So you're just applying Snell's law twice on that problem. Could I clarify what question 2 is asking? Yeah, if you go right up and stand by a window, you can actually maybe see a double reflection, slightly displaced. And try it with something like a pin. Maybe I'll go do it on the window of the room I'm in right now and see if I can see it. You won't be able to see it, but actually, I can see at least 3 slightly displaced reflections at the window I'm at right now. Now, it happens to be a dual pane window, but um, be thinking about that. And by the way, a transparent piece of glass actually reflects some of the light that falls on it. So if you've got light that is shining at this thing, some of it's going to bounce off of here. And some of it, well, I'll let you figure out what else can happen. One of the things you can do when you're making a telescope mirror is, like, if you've got your concave mirror ground for the telescope, but you don't want to start silvering it yet because you don't know about its quality, you can take the unsilvered mirror and put it into your telescope and go out and look at some bright star, like say Vega, or I don't know, Arcturus, or just some bright star, and that unsilvered mirror will reflect enough light that you can get a decent image of those, and you can look at the image of the star and know, you can see if your mirror has flaws in it and stuff like that without having any silvering on there, because it'll reflect a high enough percentage of light, even unmirrored, that it'll let you do that. So if you're at home tonight, it's nice and dark out there, at least where I am. I don't have any, I can look out the window from the room I'm in here and not see any lights from any neighbors. I've got a neighbor about 150 yards away through some trees, but I can't see his lights from this window. So if my room's nicely lit up, I go over there and I put my hand up by the window and I just saw 3 reflections of it. So try that out. Let's see. Well, we talked about just about everything already. Question 8. Is that the fun one? Oh, yeah, it is. Okay. Um, this one, you're going to be applying a particular equation 3 times, and that equation actually works on the 2 optical surfaces that you have here. You've got a lens here, and then over here you've got in this case, a convex mirror. It says it has a negative focal length, and so that means it's going to reflect light. It's not concave like the telescope mirror was. So anyway, you have some object 1 meter to the left of this thing. So here's your first object. Okay, so light is going to travel from this object through this mirror, and it will form an image somewhere. Okay, that image of the object formed by this lens is going to be the object for this mirror. Okay, and there's 2 possibilities. If the image of this object forms between the mirror and this thing, that means that it forms less than 1 meter away from this lens, because they're separated by 1 meter, then it'll be on this side of the mirror, and it'll act as a real object. Okay. And when you're figuring out where that thing's going to be, you'll be using 1 over s plus 1 over s prime plus 1 over, equals 1 over f. And you're given the focal length of the lens. You're given the distance between the lens and the object, so you'll be solving for s prime. And then you'll have an object for this mirror. If its object is in front of it, let's see, where's my formula sheet for these things? Here we go. Then you need to be thinking about the mirror. And the mirror, for one thing, it's got a negative focal length because its center of curvature is behind the mirror. It's back here. That's its focal point. So anyway, negative radius on this thing. So make sure you're aware of that. But then you can figure out the 1 over s plus 1 over s prime equals 1 over f for the mirror. You'll have to figure out how far is it between the front surface of this thing and the image of this object, which is going to be the object for this. And that's tricky to understand. The image that this lens forms will be the object for this mirror. And we have to be reading something really careful. Up here, it's got S for the object distance. It's positive if the object is in front of the mirror. Front is the side the light's on, okay? So if the object is on this side of the mirror, it'll be a positive object distance. This is the front of the mirror. It's the side that the light is acting on. This is the back. This is the side for a mirror that the light never gets to. Okay, so front and back. And this mirror is going to form an image. Where is that image going to be? And so that's what you need to deal with next. And you'll be using this equation then. And that image that the mirror forms will act as an object. The light's going to be bounced back this direction, and it's going to act as an object for this thing again. And so then you'll have to reapply this equation, but you'll have to figure out, okay, how far from this mirror does the image it forms show up? Or yeah, what's the distance from this mirror to where its image forms? And if it's in front of it, great. You've got a real image here that can serve as a real object for that thing. If it ends up being in back of it, you've got a virtual image, and you'll need to wrestle with just how you're going to deal with that. And does the lens care if it's a real or a virtual image? Okay, that's something for it. All it really cares about is if the image that it's going to use as an object is on this side of it. As far as the lens is concerned, it's real. But if it's behind it, it's going to be a virtual object. And you'll have to use the sign convention for a lens for a virtual object. So that's something that you get 3 tries or 3 things that you have to deal with on this particular question. And there's going to be a magnification from this. Okay, so that's one magnification. And then the image that this forms, when the light's headed that way, will serve as the object for this thing. And that object is going to have a magnification. And then there's going to be light bounced back in this direction. And there'll be some kind of an image formed somewhere. And this and that image produced by the mirror will act as an object for the lens again. And then that's going to show up somewhere, that object, that image will. And you can figure out what's the magnification of that image. And so you'll have a magnification due to this thing the first time, due to this thing, and then due to this thing the second time. And the total magnification is the product of the 3, because half as, if say it each one makes it half as big, it'd be down to 1/2, and then that gets multiplied by 1/2, and then that gets multiplied by 1/2, and you'd be down to 1/8 the size of the original. But I don't think that's what happens. I think you may have different numbers than that for the magnifications, but it's a complicated problem, and you have to be very careful with the focal length of this thing and the signs of the objects. And also, if you have an image sign, the image value come out as a negative value, that means it's a virtual image. And so you have to be careful with those things to try and deal with them. So it's a good multi-part problem. And, I did one the other day on, as an example, but it only had 2 things in it. It didn't have a third thing that you had to mess with. Okay. Does anyone have any questions on the lab? It's mainly just a lot of somewhat repetitious work. The lab is question 7. What is question 7? Where did I? Okay. Okay, first of all, we need to know what a biconvex lens is. Okay. This is a biconvex lens, actually. It's got 2 convex surfaces. But this one, you're told that one surface has one particular radius of curvature, so 14 centimeters, and the other one has a radius of curvature of 22 centimeters. So it'd be flatter, the other surface. And so you've got different radii of curvature. And then you're told the index of refraction of the glass is 1.55, and you're supposed to calculate the focal length of the lens. Well, that's the lens maker's equation. And assume, well, you're given the index of refraction of the glass, assume that the lens is sitting in air. Okay, so just like the lens maker's equation, wherever it is, back in chapter 34, is you're given everything you need for it, actually. You just have to read those things very carefully, wherever it is. Oh, actually, there's example 3411, at least in the 13th edition, has a nice example for a 2-lens problem. And you just need to kind of extend that. Oh, there's the Lensmaker's equation. Looks like this. 1 over f equals n minus 1 times 1 over r1 minus 1 over r2. And you need to read this very carefully to figure out the signs of r1 and r2. And let's see. Yeah, you go through the calculation, and remember, this calculation doesn't give you the focal length, it gives you the reciprocal of the focal length. So you have to do that. But that's all problem 2 is having you doing. And I think it has you do it. Let's see. Yeah. You start off with maybe the light going in this direction and figuring out the focal length. And for part B, you do it for light going in this direction. Or you can just imagine flipping the lens over and having it hit this face first and then that face. So just be careful in that calculation. Well, wow, I think we talked about every one of them. Haven't seen any questions about the lab yet. I'm thinking all the tasks on the lab, this is the Jupiter's Moons lab, are not hard, just repetitious, I guess, because you make a graph for each one of the Galilean moons and then figure out from each one the orbital period of the moon. And for the radius of its orbit, and we're treating them more or less as circular, just take a look at your data and find the largest distance away from the center of Jupiter that you ever catch the moon. And each one of those, you know, if you're doing every 2 hours like you do for Io, I think was what it was, maybe you'll get lucky and actually pick one of those shots was actually taken when it was the most distant from Jupiter. But if you weren't, you probably got one that was pretty close to the most distant thing. And so use that and ignore the signs on those distances when you're doing this, because you don't care if it was far away on the left side or far away on the right side. You just want to select the one that was the farthest point away to get the orbital radius. And it's kind of repetitious, but then given those things, you can figure out the mass of Jupiter. You do have to do some unit conversion, of course, but you'll get a mass of Jupiter, estimated mass of Jupiter for each one of the moons. And the mass of Jupiter is no secret. And so if you look it up on Wikipedia or in the back of your book, and you know, you'll see what the value is. I don't have it off the top of my head. I think it's about 1.99 times 10 to the 27th. Nope, it's 1.90 times 10 to the 27th. Anyway, if you're doing something and you've got come up with something times 10 to the 30th, check your math. You've got an error somewhere. And we found one last week where somebody was off by a factor of 2. I think they were, maybe they'd looked up the radius of Jupiter instead of the diameter. I can't remember. But anyway, it showed up by the time you cubed whatever value they were dealing with, you ended up with something that was off by a factor of 10 or so. And watch out for errors like that. Okay. You have to find the actual orbital period of each moon and compare this with the orbital period we recorded. Yes. And they're not hard to find. Let me show you how I would find them. Let's see. I'll go to Wikipedia first, and I'll switch the view over here to Wikipedia when I find it. I've got it on my shortcuts tab. Let's see, so do a new share here. Let's see. There we are. Okay, so here's the homepage of Wikipedia. It's got an article about Bob Dylan on there, one of my heroes. Anyway, but search Wikipedia, and I'm gonna, just for the heck of it, pop in Galilean moons. Whoops, for some reason I've got caps lock on. Whoops, gal. Okay, 4 largest moons of Jupiter. I don't know, maybe they've got a separate article on that. They do. Okay, they've got pictures of each one of them. Io's up here at the top. It is the most volcanically active object in the solar system, and that's because it orbits closest to Jupiter, and the tidal forces on Io are such that they just keep its interior churning all the time in uneven ways, and it just, the interior boils and vaporizes and comes pouring out onto the surface. So it keeps turning itself inside out. May have some, it's got some nice history on them anyway, but where's Io Europa? Let's see. Orbit animations. It's got that, you can look at that, but it's got an article on Io. Let's see. I don't know that. Okay, so this may not work for this kind of a neat picture. Selected moons of the solar system to scale. Okay, it doesn't look like it has information on the orbits. So instead of looking them up as a whole, or wait, what was that table? Ah, it does have them all. Okay. It's got the semi-major axis in kilometers. You'd have to, yours will be in meters, so you'd have to do that. And the orbital period in days. So you'd have to do a little bit of unit version there. Or I bet if I looked up Io by itself, moon of Jupiter, and all these things also have, but it'll have discovery, designations, orbital characteristics. Okay, so it's got periapsis and apoapsis. Those are for when it's closest and farthest from Jupiter. But it's got its mean orbit radius, which is 421,700 kilometers. Well, if you multiply that times 1,000 meters per kilometer, you'll have the value in meters, which is something that you had. And then it's got the orbital period. Oh, let's see. Hmm. Here we go. Oh, yeah, actually, that's what you want, is that orbital period. I was trying to think, sidereal is with respect to the stars, and that would be the true orbital period, although it's not going to differ much from its orbital period with respect to the sun, because Jupiter's so far out. Anyway, so you can find those orbital periods. And I don't think they'd be on the back of your book, but Wikipedia is the world's greatest ever encyclopedia. And if something's wrong up there, somebody will find it and let them know, and they'll fix it a whole lot sooner than the next edition of the Encyclopedia Britannica would have ever come out. Those things came out about every 5 or 10 years. So something like that. But it's like this has been run through the check mill often enough that it shouldn't be a problem. Yeah, but anyway, the as part of your calculations and results section, you can have that, or you can have it in the, you might put it in the error analysis section where you compare the orbital radii of your moons to the actual one, because we were doing a pretty crude observation to try and figure these things out. And the data that's up there on Wikipedia, some of it may have come from the Galileo spacecraft that was actually orbiting Jupiter for quite a few years and got really accurate data on all of its moons. So those are things that are better known now. But if you come out with some somewhat wonky values for the mass of Jupiter, and they're not going to be that wonky, actually. People are always, you should certainly get the times 10 to the 27th kilograms part right. And if that doesn't come out right, you've got a serious error somewhere. But you should also be pretty close to 2 and maybe even 1.9 sometimes. And I've had people just with the data that they had get really close to the correct value. And so you should be able to do that. But if they're a little bit wonky, go and look at the data that you have for the moons, especially if your average value is a little bit weird. Check out the average value or the values of your moon periods and moon orbital radii. And maybe one of those things is a bit weird, and that would kind of skew your results. So try to figure those out. Okay. Any other questions for tonight? I'll be, let's see, I think I have to go into Spokane in the morning, but I should be back in the afternoon, and I can check and see if people have any other questions that have popped up between now and then. And you have till midnight for both of these things, so should be able to do it. These are all doable problems. They're going to take some care, especially when using that Lensmaker's equation for one, and then number 8. Be extremely careful. And I saw in the textbook somewhere as I was glancing through here today, they talked about spherical aberration. And it's what happens when this would be the nice axis of action. And as long as your light rays stay close to this axis, spherical aberration isn't too much of a problem. But if you start having things that are way out here or way up here, that's when images can start to get kind of weird. And we haven't dealt with that at all. Let's see, Alyssa has a question. What is the question, Alyssa? Oh, on the lab, it says it can be accepted late up until Monday. Yeah. Oh, yeah, it'll still have a 20% reduction. So, yep. Yeah, it's on sale from 11:59 p.m. tomorrow night until 11:59 p.m. on Monday. It's on sale for 20% off. So I was talking to my one of my granddaughters, and yesterday was her birthday. She's just turned 9, and we'd sent a couple of packages down there to her. There was one package that had a bunch of stuff that was for her older sister. Their birthdays are only a few weeks apart. And then there was this other stuff, and she said, "Is that stuff for me, or do I have to share it with Briella?" And I said, "Well, it would be nice if you shared it with Briella, but it's for you." And she said, "Okay, I just wanted to clarify that." And I was stunned. This was a kid that just turned 9, and she's using the word clarify. She's a bookworm, so it's kind of neat. Anyway. Okay, well, I'll let you go back to work on these things. This will be pretty good. So I'll be posting the next homework, which is on the interference and diffraction, the physical optics stuff. And next Tuesday, let's see, we do have a THINS lab that I want you to do, but I also want to show you a bunch of demonstrations for diffraction and interference effects, because some of them are just kind of mind-boggling, and it's kind of fun to look at that stuff. So I'll be doing that. Okay, I'll pause the